Hello everybody. The topic which I'm going to explain you today in this video is about the theory of laser. We all know that laser stands for light amplification by stimulated emission of radiation. So if I talk about the parts, the important parts of a laser will have three important parts. The first one is active medium, which I am actually drawing like a rectangle here. And there will be something called a pumping source which pumps either by photons or by electrons this medium to achieve something called population inversion. So we'll also have something called pumping source, and this one is active medium. And we will also have feedback mirrors for this active medium to actually kind of make the photons in this active medium to actually bounce back and forth and get amplified and give some intense coherent light source as output. So anyways, we'll actually deal with the mathematics that we actually care about when we talk about lasers. So what I do is I actually take some kind of cylindrical bar of material which could be having the it should have been actually more perfect, but let's assume that this is actually perfect cylinder with the cross-sectional area as S and the length as L, and I'm going to actually pick up small slice of this one which I'll call as dz thickness, dz as its thickness. Then I'm gonna put some kind of marking like this because this is my region of interest, and in this if I have got f number of photons here, and let us say that for traveling of these photons through this small slice of dz thickness, if the photon number becomes f plus df, then I can talk about the change that has happened because of the traveling as df for the photon number. So if I actually kind of draw the change of photon flux, photon number per unit time, then I should be talking about df into s, because f photon flux actually is number of photons per unit area per unit time. So this quantity, if I write, this actually tells you that change of photons per second. And remember, this change of photons per second happens because of two main processes that are actually stimulated emission and absorption happening inside this material. And if I actually kind of think that this material is made up of two level atoms, then I can write, I can make use of the rate equations which I explained you in the earlier video. So because of that, I can actually write W21. This is actually because of stimulated emission, and then I can also write the number density of the upper level, and this is actually because of stimulated emission, and because of absorption I will have loss of photons. That's why I'm writing minus sign here, and W12 here, and N2 again. Sorry, this will be actually N1 because absorption is proportional to the number density of lower levels, and I should be multiplying this quantity with the volume because these are actually number densities. That means number of atoms with level, with electron sitting in upper level per unit volume. So this should be multiplied by volume element of this slice, that is actually S into dz, to get the same dimension formula as this one, which is per second, number per second. So I can actually easily actually cancel out S on both sides because it is there. So if I write this one for df, And also I can actually write these W21 and W12 in terms of their definitions involving the cross sections. So this can be written as sigma 21 into the photon flux F and N2 minus sigma 12 into F into N1, and outside of this one I can write dz, right? And what I can do is I can actually take this common EF as common factor out because it's there in both the terms. And also I think I can take sigma 12 as well as common factor. So if I take maybe sigma 21 also common factor, so this sigma 21 into F here, and here it is N2 minus sigma 12 divided by sigma 21 into N1. So this is what I get for, of course dz is there here as well, and this is what I get for df. So I can write this quantity for df by f. df by f is equals to sigma 21 into N2 minus, I think this ratio we have seen in the earlier class that it was equals to G2 by G1 and N1 into dz. So this is what we get. It's coming out like a kind of differential kind of equation, and of course I can actually do integration on both sides, I think, but let me quickly see that to have this df quantity as a positive number, so to have this df as being greater than 0, then I should expect this N2 minus this quantity which is there in the bracket to be more than 0. That is N2 minus Z2 by Z1 into N1 should be greater than 0 if we want to have this condition. So that means I should have my N2 being greater than Z2 by Z1, which are actually degeneracies of level number 2 and level number 1, and the number density of lower levels. So this is what I should get. But naturally what happens is, if we actually take their ratio, the ratio of N2 and N1, let me do it somewhere here after erasing this. So if I actually make use of Boltzmann's statistics to write the ratio N2 by N1, then I should be actually writing involved in the exponentials that is actually like this. So if I write N2 by N1, this is equals to Z2, the degeneracy of level 2, and Z1, degeneracy of level 1, into exponential, here we should be writing minus E2 and minus E1. This is what we should be writing, and divided by KT. So this is actually from the Boltzmann's statistics. So if we actually remember this condition for the two-level atomic transition, which is E2 minus E1 is equals to h nu, the photon energy, then this N2 by N1 is equals to Z2 by Z1 divided by 1 by exponential h nu by kT. So this thing, we will always have this N2 by N1 being less than this quantity G2 by G1, G2 by G1. It's always less than this one for any temperature which is actually non-zero. This is what happens actually for as a natural consequence of thermal equilibrium. So at thermal equilibrium we always have this N2 by N1 less than this quantity G2 by G1. That means we'll always have population sitting in the lower level predominantly. But if I have this condition, then we'll not be able to have any kind of df being greater than 0. That means we'll not be having any amplification of the photon flux. So to have amplification of photon flux, we need to actually create a condition where this n2 by n1 is greater than this quantity actually. So the way we achieve this thing is actually called as pumping. So if you do external pumping to the sample of two-level atoms, of course that's what we're considering here, then we can create a condition where n2 is greater than n1 in a way, and that's the condition which is called as population inversion. So we are inverting the population level, which is being minority to majority for n2s. So we want to make majority of n2 atoms. So this is called population inversion. So population inversion is a condition where we achieve this inequality. So okay, so having said this, we're going to actually integrate this differential equation on both sides by taking the limits of integration as maybe as f0 photons at the left hand of that cylindrical bar which we considered. And so let me actually kind of draw the thing over here again. So this was what we had here, and we considered this small slice as dz here, and if I assume z as its direction here, then length of this one was L, and I can actually say that there are actually f0 number of photon flux in the beginning. Then what happens to the photon flux at the end of it, which could be f number here. So I can actually differentiate this equation, integrate this equation between the limits f0 and f, and df by f is equals to this entire thing as it is, sigma to 1. But of course I can also, this is actually property of the material, which is actually the cross-sectional area for emission, stimulated emission, which is actually the characteristic constant of the sample, so it can be written outside, and n2 and these things are also constants for now, so we can write even these things also outside the integral, and I can put dz here, integration dz. But I am saying that this is actually from z is equals to 0, which is the left hand of this cylinder, and then there could be z here, which is equal to L here. So this is actually from 0 to L and dz, that's the integral here. And remember, for 1 by f, I think the integral is natural log f, and between the limits f0 and f is equals to sigma to 1 n2 minus z2 by z1 into n1, and over here it's L. That's the integration after doing integration and applying the limits. So here we can get ln f minus ln f0. That's actually after putting the upper limit and lower limit. But log a minus log b is log a by b. That's why I can write this quantity as ln f by f0. And of course LIF by f0 will be having the base as he here. So if I actually, of course, this side entire thing is same for all these steps which I explained in air. And this if I write for f by f0, then this should be equal to exponential of this entire thing, which is e21 into n2 minus z2 by z1 to n1 L. And what I can do is I can send this guy f0 towards the right hand side and write for f. So if I do so, I'll get f is equals to f0 into exponential sigma to 1 into n2 minus z2 by z1 into n1 into n. So what is this telling? It is telling that if I start with f0 photons at the end of, left hand of the active medium, we can call this, because this is actually the thing in which we are getting the population inversion. But anyways, if we start with f0 photon flux at the left hand of the active medium, then after a pass through this, after a single pass through in the sample for a length of L, I'm going to have the photon flux f as f0 into this factor. Okay, so yeah, this is actually fantastic. And now we consider that we are having some kind of amplification because of this n2 being greater than this quantity. So we want to make that amplification even further, I mean even more. So for that purpose, what we do is we place this active medium between two mirrors, and we will have something called reflectivity for the mirrors. That is actually the uh, power reflection coefficient. So I'm going to call this thing as R1 reflectivity and this mirror with R2 reflectivity, power reflectivity, or maybe yeah, intensity reflectivity we can call. So and let me erase this one. And when we have this photon flux traveling through the sample for a length of L, then we might have some internal losses. So those internal losses we actually uh, call as L sub I internal, and those could be because of defects in the sample. So yeah, I'll call Li as my internal loss, internal loss for a single pass through to the sample. And so let us say that over here we have got F0 as our photon flux, and now I'm going to actually calculate the photon flux after one round trip inside the material, inside the optical arrangement of the mirrors. So I will call this arrangement of the mirrors as cavity, laser cavity. So in the laser cavity, if I start with F0 flux here, then what happens to the flux after one round trip through the uh, laser cavity? So it will start from here, it will go all the way, and it'll actually pass through this one, and it will hit this second mirror here, and it will bounce backwards and travel again in this active medium, and hit this left mirror, and again bounce back and come to the same point at which we started. So for that one round trip, the flux could be, let us start with F0 here. F0 is the starting, and after traveling through the length of L, it will acquire this quantity. So it will be having e power sigma 21, and I can even drop this sigma 21 factor here and just call sigma 2 for simplicity of writing, I think. So this is a sigma here, and this is actually n2 minus g2 by g1 into n1 into L. This is actually for one round trip, and of course, as I said, there will be internal loss of Li. So after loss, we will get 1 minus Li as the remaining photon flux, and this will go and hit this second mirror. So after hitting the second mirror, we'll get R2 into this much of photon flux coming backwards into the material. So this will come and it will again pass through this. So because of one pass through, we had this one, and because of next pass through, we'll again have same kind of factor here. So this multiplied by something we have to write, but space is less, so I'm writing here. So this is exponential sigma n2 minus z2 by z1 into n1 and L here. So this is actually photon flux after starting from here, going up here and hitting this one and coming back here. But again, for the second pass through the material, we'll have internal loss, so we should write this term again, Li, and this is going to hit this R1 mirror now. So this is actually, after hitting R1 mirror, it'll again come back to this point. So this is actually the photon flux after one round trip in the material. So if I call this quantity as F prime is actually the photon flux after one round trip inside the material. So I'm going to put this call. Sorry for that disturbance. I had a phone call from somebody. I should have put this in earphone mode. But anyways, airplane mode. But anyways, let me come back to this calculation. So if I call this thing as f prime, then my f prime can be actually written as f naught into r1 into r2 into 1 minus li squared into exponential 2 sigma into minus n g2 by g1 to n1 into n. So this is what is my f prime. But if I want to have this photon flux as steady, if I want to have that photon flux as steady in this laser cavity, then I should be having the initial photon flux being same as this f prime. So if I want to have something called steady state, maybe, or we may even call threshold, or maybe critical condition for laser, I think. So so if I want to have sustained oscillations inside this, I mean if I want to have steady output from the laser, then I should be having this f prime being equals to f naught, because we want to have that steady, though it is leaking a bit from this R2 mirror, because we expect this R1 to be 100% reflective mirror and this one to be 99.9% mirror. So after round trips, what happens is we'll have a condition where we'll have some slight leak of photon flux here, but that leaked photon flux should be compensated by the gain inside this material. So if I want to have f naught is equals to f prime is equal to f naught, then we can see f naught gets cancelled here, and we can write some equation like r1 r2 into 1 minus this one 2 sigma into minus z2 by z1 into n1 into l is equals to 1. And this is what we call as a threshold condition for laser. So if a laser if this alignment is called laser, so if a laser achieves this condition, then we call that it is a threshold. And this quantity n2 minus n1, when we reach this n2 minus z2 by z1 into n1, I think this condition when it is equals to let me actually say that this condition I think is this we can call as delta nc, which is actually critical inversion. So this is called critical inversion. So if we want to write the equation for critical inversion, then we can actually make use of this equation and write that. But anyways, let me actually erase some space here and write that expression. So what I'm saying is, at threshold we'll talk about something called threshold inversion, which actually the difference of this and this, and that we can write mathematically by using the equation which I put in the box right here. So exponential stuff, if we send all this thing towards this side, can be written as exponential 2 sigma, and this one is delta nc, and L being equals to r power minus r1 power minus 1, r2 power minus 1, and 1 minus li power minus 2, because these are having 1 and 1 as powers, this is as 2. So if they go towards the right hand side, they will get minus on their top. So, and if I write delta nc from this, of course I can put 2 sigma also here and L here. This will go and make ln of this entire thing, right? Ln of this entire thing which is there here. But I can make use of ln ab is ln of ab is ln a and plus ln b. So this is actually property of logarithms. So because of that, we can write all these three terms as ln's. So this will be ln r1 power minus 1 plus ln r1 power minus 1 r2 power minus 1 plus ln 1 minus li power minus 2, and this is what we have here. But if we write for this delta and c, this will be 1 by 2 sigma l into, over here if we have, I mean it's a property of logarithms, that if we have ln some x power n, then ln some x power n, then we can write this thing as n into ln x. It's a property of logarithms. Of course, it comes again from the same thing which we used, ln ab is equals to ln a plus ln b. So anyways, because of that property of these logarithms, we can write this thing as minus ln r1 minus ln r2 minus 2 times ln 1 minus li. So this is actually the equation which we call as threshold inversion, condition for threshold inversion. So in brief, what happens is, in laser we'll have three components. The first one is called active medium, in which we actually try to achieve this condition of n2 being greater than g2 by g1 into n1. That's because of course, this we call as active medium, and this condition is actually achieved with the help of something called pumping source, which could be a source of photons externally, or maybe source of electrons. That's because of electrical bias amplification. And we will also have some feedback mirrors for the amplification of the photons after fewer round trips inside the material. So yeah, this is actually kind of schematic diagram of a laser, and this is the principle of laser. So the principle of laser in brief is this one, and in this what happens is, initially we will have spontaneous emission happening in the two level systems that we consider. So electron sitting in the upper level of an atom will actually come down spontaneously, and it can go in all possible directions. But if that photon goes towards this side, then what happens is it can stimulate the other atoms, two level atoms, to actually kind of amplify. So the stimulated emission makes the photon number amplify, and again those photons again go and hit the next atoms and make them stimulated emission. So that's how, because of stimulated emission, we go on having amplification of the photon number, and those photons hit this mirror, and when they come back again, they again make the amplification process even more. So that's how this actually kind of after round trips we actually go on increasing or amplifying the photon flux, and of course this mirror will be actually slightly less reflectivity than the perfection, so it will be at 99.9% reflection, and this is at 100% reflection. So we'll have some small leak from this one, but at steady state what happens is this leak of photons and the gain in the photon inside will actually balance, and we achieve something called a threshold condition, and which we have seen in the case a while ago. And at that point we actually start having constant photon flux inside the cavity. This is it in this video, and I will meet you next time with some other video. Thank you for watching. Bye bye.